Four. Okay, good. See, so about at the last 2 weeks, I kind of like we did uh, the stuff related to this topic actually, the multivariate analysis. Multivariate analysis should be done ahead of the time actually before we're going to get into the principal component or the other one. But the way that they have structured, I cannot do nothing. I just follow the way that how they have been uploaded the material for every week. So the multivariate or multivariate, that one has to be done before that. We're gonna go ahead and do that principal component as well as the repeated measures, because they both can be handled with the aid of this multivariate analysis. But anyhow, let's try to build up some kind of a knowledge what's going on behind this one. This is a kind of a, like extension of the univariate analysis. Instead of having a like a y means the dependent variable. Keep in mind the dependent variable becomes, rather than one variable, it's going to be a whole bunch of variables, call them, and in that way it becomes like a multivariate. Okay, the dependent variable, whatever that reading you're going to take, that one, instead of taking on one variable, you're going to take the readings on several variables at the same time. Let's say that you can remember in a regression, you can think about that one variable, the height or the weight, being that explained through the weight. Okay, sorry, the weight being explained by the height, that weight versus height. And instead of that keeping that same dependent variable, the weight, height, you can that multiple, that you can get the multiple regressive variables. In that particular scenario, it becomes a multiple regression. It's not multivariate. It's not multivariate because your dependent variable still univariate. You're still interested in the weight, but you're gonna see that how, what are the other variables gonna affect to the weight, like that, or the monthly income, or whatever that variable that you are interested in being explained by the other regressive variable. Even though you have a whole bunch of regressive variables, still you have a dependent only one variable. But let's say at a certain point, instead of one variable, you are planning to have a look at it two variables for the dependent variable. That's where the multivariate analysis comes into the picture. Okay, that's how we're going to build up that one. From now on, that we're going to take into account all the variables, dependent variables at the same time, and tackle it. So before we're going to get into that, let's get like a clear idea what's going on, and then the theory behind that one, then how it looks like. Okay, you can remember when you have one group, if you want to run any test to check and see whether this mu equals to mu naught. Mu naught is a given variable, sorry, given parameter, given or non parameter. See, this is the population mean. Population mean has been given at a certain point, and see that whether that can be tested against its counterpart. For that particular scenario, for that test, we are using this test statistics. Can you remember? Y bar related to that population. The sample for the population, we're going to pick a sample. That sample has like a mean. And for this one, you, instead of for mu, you have to subtract mu. Instead of mu, you're going to subtract mu naught, because you are assuming that H naught is true. It's called the under H naught. And divided by S divided by square root 10, that should be distributed according to this T distribution with the degrees of freedom n minus 1. Here, this one is calculated like this way. See? You have a reading minus its mean square and this one. This part we normally call the sum of squares. See, sum of squares. Or within, sometimes we can call this one within. This part we're going to call the degrees of freedom. See, this is the degrees of freedom. This is the degrees of freedom again. See, at the same time, y bar calculate. That's a basic stuff that we have seen. Now what we're going to do, we're going to square that one. See, I'm going to square. If I square that one and it looks like this, same thing, I'm going to square. I'm going to take this into the numerator, and this, I did some kind of adjustment. And at the same time, I split this one. See, I split this one and write this one right before and right after this guy. At the same time, I'm going to take this to the numerator. Every term has been taken into the numerator. When you've been taken to the numerator, you can rearrange like in this format. See? This format. See? And that should be distributed according to F distribution with degrees of freedom 1, comma n minus 1, n minus 1 coming from the here. Okay? If you have one group, okay? If you have one group, n minus 1. See? With the degrees of freedom for numerator 1, degrees of freedom of denominator is same as the degrees of freedom of T distribution, which is n minus 1. See? See? Like that. So now what we're going to do, we're going to have a look at it, its counterpart, the multivariate analysis, multivariate one. Instead of one mean, we're going to take into account several means. Let's say that test 1, test 2, test 3, test 4, test 5, several tests being taken into account, and have a look at it and make some decision for certain certain scenario. But for that one, you rather than going for individual test, you can take everything into account. That's what we're doing in the multivariate analysis. See? This time, for the same thing, I'm going to have a look at it, its counterpart, multivariate counterpart. See? This time, t squared, instead, we don't have a t in this case. Remember, there's no such thing for the multivariate. We start from the t squared, which is in number of observation. See, look at the vector, y bar, not y bar vector. See, y bar vector minus, not mu. See, this vector 2 by p. This one, sorry, this one, I'm sorry, p by 1, p cross 1. Okay, that's the size. So here, see, I'm just get the analogous expression for this one in the multivariate case. See? S squared for what? Variance. This is for the variance. But in multivariate, we normally call this whole thing variance. This is a variance matrix. I'm going to write the matrices in that this fancy way. See, like this way, negative. So that means that it has been raised to the power of 1 inverse. And this being, instead of this one, you cannot keep this one like the way that it is, like the way that we have in univariate. You have to get the transpose. So those are matrices. Okay, those are matrices. This one has been named after that Harold Hartlin's t squared. This one is called the Hartlin's t squared, and this one distributed according to this distribution. See? This distribution. This t squared distributed n minus 1 times p. N stand for the number of observation. P stand for what? Number of variables. How many variables? See, p many variables you tackle. If you have a 2 variables, test 1 and test 2, do you have a 2 variable? In the beginning, you have a 1 variable. See, p equals 1. So now p equals, we're going to go with the general formula. See, this one. Having degrees of freedom for this guy, and this is for the denominator. See? And if you're going to rearrange, on the other hand, you can write the f in terms of t squared. See? I'm going to get the n minus p to here and divide by this one. And then I can write the f, which is same as p. So if you want to convert the t squared into f, you have to multiply by this factor. That will contain the degrees of freedom for the numerator and denominator. See? Okay, like a rough idea. Okay. To get a idea, say, let the data matrix for a random sample of size n equals 3 from a bivariate, 2 variable. Normal population be like this. See, you have a 2 variable. See, 3 observations. 3 observation, 2 variable. Okay, y1, y2. See, it's a matrix, 2 by 3 matrix. This is my y. See, whole data. See, this is the first observation. Second observation, third observation. It's a test 1, test 2. Student 1, student 2, student 3. See, that instead of looking into test 1 and test 2 separately, I'm going to look into that 2 test or some other, whatever the variables that we are interested in. They are that the analysis we can take into account at the same time, see, simultaneously, without doing this one separately, one at a time. Rather than doing this one at a time, you can do both. Now we're going to say evaluate t squared for this one. See, our this one has been given. See, observed, see, known, this guy has been given, see, it's been given. It has been given as a vector. Vector has been given in transform form because it's a now row vector. It has to be column vector. See, that's the sampling distribution of t squared in this case. So we can easily say get the y bar, see, y bar vector for the y1. You have two variables, y1, y2. See, y1, see, y1 bar you can get adding that these numbers 6 plus 10 plus 8 divided by 3. The other one, observation 9 plus 6 plus 3 divided by 3. And you still have a 2 by 1, 8 and 6. See, the averages. Now you really need what? You really need the variance of y1. Variance of y1. How do you get the variance of y1? You go to the reading. From your reading, you're going to subtract its mean, see? And square plus. Go to the second reading. For the one for this variable, okay? I'm doing one at a time. And divide by and subtract its mean square plus third reading for that variable and get the whole thing and divide by n minus 1. Y2 here, n minus 1. You can remember how many observations? We have 3 observations. Okay. We have 3 observations. So n minus 1, that's why 2, we get this one. In a similar fashion, you can do this one. See? And we will go to this one, 9 minus its own mean, which is 6 square plus 6 minus 6, next reading, square plus 3 minus 6, okay, square, and divided by n minus 1, which is 2 plus 9. Now you get the covariance between those two. There's a covariance. How they were correlated. See, simply you get 6 minus 8 times 9 minus 6. See? n minus 8 times 6 minus 6 plus 8 minus 8, 3 minus 6, divided by n minus 1 again, you get 2. That's how you're going to build up the covariance variance matrix. This is the variance of y1, this is the variance of y2. These two are in this minor diagonal. These are called the major diagonal, major or main diagonal. This one is minor diagonal. See, on minor diagonal, you're going to have the covariance that's being repeated. Or if you want, you can take only the upper triangle or the lower triangle. It doesn't matter. Then you can find its inverse. We don't have to do by hand, but I'm showing you. You can use that because we do in program. This one, in a case like this, very easy. What are you going to do? If you need the inverse, you're going to find the determinant of this guy. Determinant. How do you find the determinant? You're going to multiply this one 4 times 9 minus 3 times minus 3. That's the determinant of this. That's the size of the S. Times, I'm going to switch these two. In a 2 by 2 case, very easy. I'm going to switch these two and then drop the negative sign of the entries on the minor diagonal. See, I drop it. Okay. It's a shortcut, but you don't have to do by hand. By any chance you have to do by hand, then you can use a shortcut like that. That's what I'm saying. For your convenience. We really need the inverse. Can you remember? Then we're going to plug in into here. See, when you get the y bar minus mu naught has been given. See, mu naught has been given. Nine and 5. You subtract, and then at the same time you get the transfer. That's why I wrote this one in this form, this horizontal form, or in a row as a row vector. See, 8 minus 9. Y bar is 8. Not first entry is what? How much? 9. See, y bar is 8. See? I'm going to subtract 8 minus 9. Come on. The other entry, 6 minus 5. And this is the inverse. And the same thing being, we're going to write this one as like a column vector. See? Get this one. Then you can see 1 by 2, 2 by 2, 2 by 1. 2 get cancel off, 2 get cancel off. You are left over with 1 by 1. That means just the entry. Just the entry. just entry. You know how to multiply these ones. See, if you multiply these two, what do you get? 2 get cancelled off. You're gonna have 1 times 2. You're gonna have a first row and 2 columns. 1 column and sorry, 1 row and 2 columns. Okay, 2 get cancelled off. Then you have 1 row and 2 columns. How do you get those? First row, first column. See, this to that plus this to that. You built up that entry. And the second entry, first row, second column. This to that, that to that. That will give you that. Then you have a 1 by 2. 1 by 2, you're going to multiply by 2 by 1. Then you have. Then you know the sampling distribution of t square being given this one. N is 3 minus 1. See, number of variables. We tackle 2 variables at the same time. This one. Get familiarized with the formulas. When you see something, you can get verified easily and then see whether you are on the right track. This one and this one, P, this one, eventually T squared distributed according to 4 terms F distribution. Okay, like that. Okay, I'm gonna come to this example later. Okay, I think something missing here. No, whole bunch of. I think something missing. Okay, that's okay. We see that. Something missing. No, some pages are missing here. Let me see. 1 second. Okay, some pages missing. Then I scan. First, let me see. After this one, independent multivariate analysis. This one. Oh, are they coming? Okay, let me see. That's the problem. 1 second. I think after this one. No. 2 pages. I'm gonna scan real quick again. I think some pages missing. Okay, 1 second. Okay. Second, I think some pages they were not separated. I think they were so sticky. Should be. It's open. Okay, I'm gonna save this one. 6:30 July. Month, very month. Yeah. Okay. Here, then we get this one. We're gonna come to this here. Then we're gonna get into the two groups. Look at the two groups. Earlier we were talking about the one group, univariate case, multivariate case. Univariate case, multivariate. Now look at the univariate. Two groups. See, mu1 equals to mu2. They are not vectors, just two variables. So two groups. See, two groups. See? So equivalently, you can write like this way. Even with that one, you have a two cases. One is dependent, the other one independent. If it is dependent, like you're gonna that measure something before and after for the same thing, like in a repeated measures. This is the beginning of the repeated measures actually. Can you remember? So here, see, instead of this one, I'm gonna say different. They were dependent. I take their difference. Difference will be tested. I'm sorry. Here it should be not equals. Okay. And in its test statistics would be like this d bar. D bar means like a whatever that difference you get the difference of that one, and difference of that two population difference you get that one, and then you're gonna find the average of that guy and the standard deviation of that guy. See, I'm gonna replace that one the same format that we had earlier. See, I put the d bar here, d bar here. Again, this one f1 and same degrees of freedom. If it is independent, we're not going to take the difference. We're going to keep as it is in a two groups, male, female. See, on a two countries, two counties, or something like that. We're going to compare, contrast. See, I'm going to divide that one by, see, this difference divide by its standard deviation. Standard deviation would be like this. This one should be like that. Okay, it's standard deviation. If sigma 1 and sigma 2 are known, and they both are known, they are no, different, and they are known. And your this part should be like this, that one distributed according to normal distribution. See, standard normal distribution. But this part in 0, because that's why that we don't have a mu part. And this difference divided by that one, case 1. And it's I think I missed that one again. That's okay. So that page didn't come again. It got stuck, I think. Hold on. I can scan separately. That page again missing. Okay. this out. Yeah, let's see this one. To group that one, let's see. This one, this one. This one missing all the time. They get stuck. One more time and see. No, that's okay. We can talk about that one next time. Okay. Give it a try because there are 6 pages, but go through. I don't know. For a certain reason, that page doesn't come. Okay, that's okay. There are 6 pages. Try to do the other page. Just one page and see. Now come. Yeah, that's the page I need. Yeah, this thing earlier that when we were here, the case 1, see, under the independent, see, when these two are known, unknown, and they were not the same, then you can plug in this one over here. And the case 2, you're going to use the T if they are unknown and not equals down. Now, unknown and not equal, see, it should be bar, and bar. They are right there. Okay. Standard deviation of that one, but this time distributed according to T distribution with the degrees of freedom like this. See, this one standard deviation is when they were not unknown, you replace them with the sample counterparts. See? But they're not equal. They're not equal. Then your degrees of freedom comes like this. See? It's the degrees of freedom. The case 2. Okay? And the third case, and this time they were known, and this time again they were not distributed according to normal distribution, but your standard deviation of the difference of means would be that this sigma can pull out because there's only one, and kind of plug in over here. And the case 4 is the one, these two, this is the most important case that we do all the time. See, they both are the same, assuming that the population standard deviation are same, but unknown. You don't know. See, you don't know. Then it's going to be distributed according to T distribution, but your standard deviation would be full standard deviation times 1 over n1 plus 1 over 2, where full standard deviation is nothing but n1 minus, see, they are corresponding, see, variances In some place, sometimes we're going to call this one W1 for this part, and this one W2, you can say. And this is nothing but N1 plus N2 minus 2. Okay, minus 2. That's a pool deviation. So this the case 4 is the one that most of the time we're going to focus on, assuming that sample population standard deviation are same, because it's a homoscedastic. This is a homoscedastic. We all the time tackle homoscedastic the cases, not the heteroscedastic. Heteroscedastic a little bit heavier. And because of that, when these are same, we're going to call that an homoscedastic. Homoscedastic, and then unknown, doesn't matter, unknown, you can replace that one with this standard deviation. Standard deviation is composed with this part and this part. This part is nothing but the pool standard deviation. See, pool part you can take and then plug in over here and get this one and plug in here like that. See? And the degrees of freedom would be nothing but the degrees of freedom of the first group plus the degrees of freedom of second group. Each group has n1 minus 1 plus the other one n2 minus 1. That's how you got this one. Okay. That's how you got that. See, we particularly interested in the case 4 where sigma 1 and 6 2 are assumed to be the same, homoscedastic, but unknown. See, but unknown. Now what I'm gonna do, I'm gonna square this one. Whatever I have, I'm gonna square. See, I rearrange this one. SP, I'm gonna plug in here. See, degrees of freedom. This one, I'm gonna square that one. This one, not this one yet. Not square yet. Not square yet. See, then I'm gonna square. I'm gonna see. I simplify inside. See, common denominator, and then I'm gonna flip it. See, I'm gonna bring this one to the numerator, denominator, the numerator, and the rest part I keep over here. And then I'm gonna square. Then this part I write here. This square I'm gonna split. See, like this. And this one I'm gonna keep in the middle. And that one, if you square, t square become F distribution with degrees of freedom 1, because we have one variable. See, we're going to talk about the one variable. See, one variable for the male and female, or one variable being measured before and after. Salaries, we're going to compare, contrast the salaries of the male and female or something like that. Okay? See, and this is the most important part. It's, see, and then SP is like this. We saw that one earlier. Okay, so then we get from there, get back to the notes. See, it's a multivariate counterpart if you go to that one. See, multivariate one is the one that now we are tackling over here. You have a two groups, multivariate two groups. See, one group has a several variables. Let's say P variable. This one also P variable inside, but two groups. Females. They are all the information, the GPA, that test 1, test 2, test 3, test 4. Then males, test 1, test 2, test 3, test 4. We're going to compare the same 10 and see that whether they have the same averages or not, or something like that. See, or equivalently, you can write like this way. See, as a same thing. Now vectors. Okay. It also have a two cases, mainly two cases, dependent and independent. But independent, we don't go to all the cases, only one case. As I said, with the some pool one, this one only. Other ones we don't have to. Okay. So in the multivariate case, what are you gonna do? The dependent case, you can remember n here. This one replaced by the split when you split that one. See, d squared, you're gonna split like this. And this will be distributed according to this one. Look at that. When you're gonna when you from this one you can get the univariate case. When p equals 1, p1, n minus 1, n minus 1 get cancelled off. Then later on 1 and n minus 1. Same thing you saw in univariate case. In univariate case, dependent one under dependent, see, univariate, when you have a two groups, two groups. When you have two groups, let's see, you saw this 1 and n minus 1. that will be easily derived from the multivariate case. It's consistent. And the independent one, we mainly consider the case 4, where population standard deviation of the group 1 and group 2, but they have their matrices. Okay, these are matrices. But they have, let's say, 4 variables of that one. Then here 4 variables. And they have the same standard deviation, variance, covariance matrix. And then, but they were unknown. If that's the case, you're going to replace like this. It's the formula for the multivariate case. This is the part you have to take into account very seriously. When you see that when you run this one on a SAS and then you want to get it that clear, that verified, you see, this is the formula. See, N1, N2. Can you remember its counterpart? If you go ahead and look at it, it's a univariate case. Univariate, but 2 groups. N1, N2 divided by N1 and plus. Same way we have that one here. And here, the first group mean minus second group mean. First group minus second group mean, but this time we have univariate because of that, because you are dealing with the scalar numbers. Here, not the numbers. These are numbers we normally call the scalars. These are vectors and prime. Here, instead of have like just a one value, you have like a covariance matrix. It's inverse, and this being given again. And this is the factor by which that we have to multiply to get distribution. Can you remember? We had the same situation here. See? T squared. T squared distributed with the 1 and n, see, 1 and n plus 1, a plus minus 2. See? This one, observe that one. This one, T squared. Should be, okay, when P equals 1, okay, T squared distributed P, okay, P equals 1, let's go to P equals 1, 1, 1, 1. So N1 plus N2 plus minus 2, N1 plus N2 plus minus 2, they get cancelled off. You are left over with the 1N. See, 1N, how much? N1 plus N2 minus 2, same as in univariate case. See, you don't have any factor in front in univariate case. That's what I want to emphasize this one too. There's no factor. These are the degrees of freedom. I'm talking about when you compare 2 groups in univariate case in a similar fashion, but in univariate case, we have this factor in front. Okay, note that one very carefully. This factor. Here we don't have that factor. T squared straight becomes F distribution in univariate case. T squared, F, same. See? Here, no, T squared doesn't become F distribution right away. T squared has to be multiplied by this factor. Or you flip that one, degrees of freedom should be something here. Degrees of freedom for numerator, denominator is this part. See? And if you, and SP is nothing but n minus 1, see, covariance variance matrix of the first group plus n2 minus 1 covariance variance matrix of the second group. See, n1 plus minus n2, same thing. But instead of that, in univariate case, you have just a number. See, we don't have a number now because there are several variables are taken into account in that first group. Okay, and then so does with the second group. See, number of this one little bit, and the same thing. This part being replaced by W1. This part replaced this one. See? 1 plus n2 minus 2. See? Look at this in example. You can get this a fictitious data shown next to represent the scores on 2 measures of counselor effectiveness, client satisfaction, and the client self-acceptance. 6 participants were originally randomly assigned to counselors who used either behavior modification or cognitive method. However, they are the behavior modification group were unable to continue for reason unrelated to the treatment. Okay, look at the again. I think some pages missing again. There's something missing there. Yeah, one page is missing. They stuck, I think. Okay. Yeah, right after. Okay, there are four related. See, no, this one too. This one. See, this one. See. The fictitious data shown on the next represent the constant two measures of the proposal effectiveness, client satisfaction, and client self-acceptance. 6 participants were originally randomly assigned to these counselors who used to either behavior modification or cognitive method. There are two groups. See, one is the behavior modification, the other one is cognitive. But within each group, there are two variables will be taken into account. That's what I'm trying to say. We used to do only one variable. One variable from this group and the same variable from this group. You normally compare y1 for this group, y1 variable, and the for second group, y1 variable only. This time you consider two variable of three variable, 5, 6, 7, doesn't matter. How many groups? Two groups. How many variables? Two variables. So you have to make sure that those indices being very carefully that are taken into note. Okay. See the modification. See, they are in the one group. Some people could not attend that one for some reason unrelated to the treatment. See, this one here only 3 individuals. See, first individual, second individual, third individual. Here, first one, second one, third one, fourth one, fifth one, sixth one. See, look at it. These are the two groups I'm trying to compare and contrast and see this gonna be they both produce the better results in that one. See, we're gonna compare this average of this one. The both average will be taken into account at the same time. Okay, the mu, your mu vector mu would be this for this one. The mu vector for mu1 vector, mu2 vector. But in order to do that one, you need this group. See, this one averages, this average, that average. See? Then covariance variance of the y1 and y2 for group 1. Group 1, I'm talking about here, okay? I'm here. I'm not going to build up yet the both yet. I'm here. See? For this covariance variance matrix can be built up in 3 methods. See? I'm going to call that one W1. Okay, W1, no, that's just this part. Just this part. Just this part. That means you go to their reading, the reading, both will be taken into account at the same time. Okay, see this one from you're gonna subtract from this one, you subtract its mean. See, its mean, and then get the it's a transpose. See, this is the formula. It's the formula. See, 1 minus 2, 3 minus 4. 1 minus 2, 3 minus 4. This whole thing I did for the what? First entry, first person. First person, normally this minus, it's mean only. This time I want to subtract they both at the same time and keep that one in a vector. That one as a vector, see? It's a row vector. Sorry, column vector, see? 1 minus 2, 1 minus 2, 3 minus 4 for the first individual, plus, and do the same thing with, now if this guy is a transpose, I got this one, I use the transpose of the same guy, plus, I go to the second individual, but he has a two entries, okay, two variable, two scores or two observation, 3 minus 2, 7 minus 4. 3 minus 2, 7 minus 2. Then take its transpose. Plus, then go to the third entry. 2 minus 2. At the entry 2 minus 4. See? Same time. I tackle at the same time. And then get the transpose. And then sum them up. See? You have a vectors, but you do the summation. You do the summation. And then, see, little bit simplify. See, then you get, okay, you get after this 1 minus 2 is minus 1. And 3 minus 4 is a negative 1. See, and its transpose is a 2 by 1, 1 by 2, plus the other one. See, this one 3 minus 2, 1, 7 minus 4, 3. See, 1 and 3. Its transpose 1, comma 3. This is a column vector, row vector. And the last entry, 0 and minus 2, 0 and minus 2. Then it's, see, then how do you get this one? See, 1, 1 get cancelled off. Then you get the 2 by 2 matrix. And this get cancelled out. That's how they build up. You have to have the same numbers over here, same column and same rows for you to get this multiplied. See, this time that first row, first column, 1 minus 1 times minus 1, 1. First row, second column, see? Second row, first column, second row, second column. I'm built in this, see? Right there. Same way here. First row, first column, first row, second column, second row, first column, second row, second column. Same thing here. First row, first column. See, only one entry I have. First row, second column, second row, first column, second row, second column. And then later on, I add these entries. See? Right there. 2, 4, 4. That's a one method. One method you can get this done like that. Let's look at the other method. Other method, I can tackle this one at the one shot. Same thing. Rather than do that way, I'm gonna no summation. I go to that y, from y, same time I'm gonna subtract the mean, their mean. How that can be done? See, you have a y vector. Y vector. I'm talking about this y vector. Oh, sorry. Oh, here. Sorry. Y vector. See, y1 vector. I'm sorry. Y1 vector. See, this one. From this one. See, from that one, you subtract its mean. It should be y1, y1. See? See? This one considered like, sorry, here. See? It's not a vector, I'm sorry, it's a matrix, okay? It's a matrix. This matrix, I'm gonna subtract their corresponding means. See? Corresponding means. See? So I go to the entry. See? I go to the entry, this entry and this entry. See? 1 minus 2, 3 minus 2, 2 minus 2. So from this is one, this one, this one. See? That's for the y1. This one is y1 for y1. This for y2. See? Y2. See? 2 by 3. See? 2 by 3. See, for y1 this way, okay? I'm gonna get this one, flip it. From this one you subtract, see, and put it in the, see, this one, and then get the transpose. 1 minus 2, 3 minus 2, 2 minus 2, see. 1 minus 2, 3 minus 2, 2 minus 2. For the other variable, 3 minus 4, 7 minus 4, 2 minus 4. See? 2 minus 7 minus 4, 2 minus, let me see. 1 minus 2, 1 minus 3 minus 4, 3 minus 2, 2 minus 2. 2 minus 2. Okay, that's right. Why here not right? See, there should be 4. It should be 4. There should be 4. 3 minus 4, 7 minus 4. Then I'm gonna flip it. See, row become column, row become column. See, minus 1, 1, 0, minus 1, 3, 0, 2 by 3. This one becomes its counterpart. This is not, this should be minus 2. Should be minus 2. Then I'm going to build up first row, first column. See, this one to this one, this one to this one, this one to this one. See, first row, second column. See, this one negative 2. First row, second column. Then this one. See, first row, first column. See, this one to this one. Negative 1 to negative 1, 3 to negative positive 1, negative 2 to 0. So this one. Yeah, this one. Right. Okay. Then negative 1 to negative 1, 3 to 3, negative 2 to negative 2. That's not right over there. Then you get 1, 1, 2. This one, 3, 1, 4, 4, 9, 10, 14. Should be 14. Should be 14, 2 by 2. See, that's another way to get this done. See. Method 3, you're going to go ahead and then build up piece by piece. See? You're going to go to this data and then build up. See, you get the variance of this one, variance of this one, and covariance of this one. Thus, you can build up that separately, the way that I'm doing over here. I'm on that first one, okay? See? See? We're gonna call that one because it's not being divided by n minus 1. That's why we're gonna call that. So you're gonna simply go ahead and build up related to this guy. Part related to this guy without having that, only the sum of squared part only, not divided by the degrees of freedom. So you're going to simply mark this one 1 minus 2 square plus 3 minus 2 square plus 2 minus 2 square. That's what we were trying to do over here in another. See, 1 minus 2 square plus 3 minus 2. See, I got the variance and not the variance, that this part. Okay. In the similar fashion for the second one, you can do 3 minus 4 squared plus 7 minus 4 squared plus 2 minus 4 squared, and add them up. That would give you this one, 14. See, 14. Early in this method, you have a 14. Yeah, see, 2, 4, 4, 4, 14, 2, 4, 4, 14. And then you get the covariance. Covariance is nothing but this one times on this one times this one plus this one times this one plus this one times this one. That would give you 4. That's a 3 method, third method. In that way, you can get a W1. See? In a similar fashion, you can do the same thing for this guy. I'm talking about this part, W2. Okay, it's the sum of squared of this sum of squared. Sum of squared errors. Okay, sum of squared actually that you read in and minus this one is sum of squared error for this one. That's what we denoted by W1 and W. Then I built up that one you built up in 3 methods. The same way this one you can build up in 3 methods. See? See? Similarly, you get the W2 like this. Then you're gonna get the pool one like this. You're gonna add those two and then divide by n1 plus minus n2 like this one. That would give you the pool one, multivariate pool one. See? And for this particular case, you really need that one. See? Then you get the pool one. See? And then you're gonna call that one as the inverse. Okay, if you want. See? You know how to get the inverse. See? This one, plugging into this formula. See? N1 is 3, this one 6, 3 plus 6. Again, mean minus mean. From the two variables, you tackle the two variables at the same time. I'm talking about here. 2 minus 8, 2 minus 5, 4 minus 8. See? They both put into vector. Is this minus 1? That mean is being again transpose. If you have a row, now you have a column. Look at this guy. See? And if you need the F, you're going to multiply by say t squared times this whole thing is F. 6 plus 3, see 6, 2 is 3, minus 1 times 21. And then F, once you plug in up to here, you can write like this, distributed. Okay. The very moment that you plug in that one, this part you cannot talk about this part. See? You cannot talk about this distribution. There's no distribution. You have a just particular value only. That's why I call that one F naught. Okay, but their degrees of freedom 2 and 6. W is another name for that one. W is called the W means within sum of squares and the cross product matrix. W means within sum of squares and cross product matrix. On the printout, you can see sometimes they call error SSCP, sum of squares and cross product matrix. They call E. See? They call that one E. See? See? 6, 8, 8, 30. See? Sum of squares product. That's the same thing. See, this one, I'm talking about this one. That one all together, put together, W1 and W2. Who's W1, W2? See, W1 for this one. In another way, that's the covariance matrix for that one. This is the covariance for matrix for that one, W1 and W2. Those two you can put together. You can put together. See, W1 and W2. See, that's how you get the pool. How do you get the variance? By dividing by the degrees of freedom. See? But when you can convert that one to, you have a different kind of a degrees of freedom. That's the degrees of freedom for T. There's no T in multivariate case. You have a T square. T square straight go to F with this kind of a multiplier. See? But then you have these two would be your degrees of freedom. Not this one. This one only here only. As the degrees of freedom at that moment to be divided by this one in order to get the pool sample standard deviation. And this is how they were related. See, T squared, how to build up. This is how you build up T. Is look at the different numbers at the different place. They look the same, they're not. Here, see, n1 plus n2 minus 2. Here, n1 and n1 plus n2 times because of that formula. This is coming from that particular formula. Plug into that one, you got this one. That would produce a different kind of a degrees of freedom for F distribution. See? F distribution. It's not what you have here or here. It's different. See? P and P means number of variables. Two variables you have for each group. For each group, you have a two variables. T equals 2 here. T equals 2. T stands for the number of variables. Okay. G stands for the number of groups. 2 also. It is also 2. See, they both are 2 and 2. If you have a 3 groups, you can say G equals 3. If you have a P, 3 variables being given, take like a test 1, test 2, test 3, test 4, 4 variables for this setup. Another 4 tests, where 4 tests being done for that under the cognitive procedure. 1, 2, 3, 4. Then you have a P equals 4, G equals 2. Okay. And that one means this is the same formula related. One shot you can get it from this one or double summation, but you don't do, we don't do anything by hand. I'm giving you a rough idea what's going on. Okay. See, 6, 8, 8, 30. Even that part we did by hand. See? It's the same thing. Okay, that's they call that one E or W. That's nothing but the within sum of squares and cross product matrix. In the same way, B between sum of squares and the cross product matrix, it is being given on that printout type 3 SSCP, sum of squares and cross product matrix for group. The group they denote by H. Is the way how they can get this. See? 18, 24, 24, 32. You can build up that one, that part. Okay? Between one, you can build up. Okay? You want a hand, but you don't have to. On the printout, we see everything clearly. Okay? This one you see on the printout. See? So then see, then you get the total. Total SSCP, total sum of squares and cross product matrix. Between sum of square and cross product matrix plus within sum of squares cross product matrix would give you this one. See? You're going to add this one to that one. 18 plus 6, 24. And 24 plus 8. Okay. 8 is 32. 32 again. And 32 plus 30. Here, 62. Okay. So this is the total one. B plus 1. Then I'm going to find the determinant or the absolute value of that guy. How do you find the absolute value total? See, you're going to cross multiply like this. 24 times 62. That's how you're going to find the determinant. 464. Then W. You need the W's determinant as well. 116. Here, I think something missing. Okay. This is missing. I don't know what happened when I put the pages. I think okay, this is what I'm gonna go to this page. Okay, I straighten this up and then upload later. Okay, so after this, I'm forget about this one for time. This page. Okay, here the Wilks lambda for our multivariate case for comparing two groups. Wilks lambda. See method 1. See, given by this absolute value plus this one, 116, which is this one. When we run this one on SAS, you can see that one. Under that one, case 1, we know that when P and G equals 2, we can use this formula. Another way to have a look at it, we can build up this from that when you know the Wilks lambda, for that it's related, F is same as that you do that calculation through the other way around. Okay, that's what I'm trying to show here. You can remember that discussion. You see, this F coming from here should be equivalent to what all the F values coming from other statistics like a Wilks lambda, Hotling's trace, Pillai trace, Roy greater statistics. Everybody should show the same thing that we got through this procedure. Okay, you can see that. Okay, when I run that one, I'm going to compare with that one pretty soon. But see, this one. This is one my major focus. This one, and this one. We got that one by doing some calculations. See? We want to make sure that we were on the right track or not, like that. See, we calculated. Okay, see, we calculated. We built up that F piece by piece. Okay, we built up that one. See, using the several methods like that. But anyhow, what I'm trying to say that with the Wilks one, that lambda, if you go ahead and check that one, see, then Wilks lambda, sorry, this page, forget about this page, this one. I need the Wilks lambda, that's okay, but I need the F related to that one. F related to that one, you can build up in a different way. See, the case one, we know that when T equals, T equals 2, so 2, T equals 2 and G equals 2, I can use this format. Can you remember I gave these formulas earlier too, that in our notes, that when we were going through the repeated measures, anyhow, that doesn't matter. You don't have to memorize or anything like that. Okay. So if you have a situation like this, condition like this is how they are related to F. This is how they are related to F. This part divided by this one. This is the factor by which this should be multiplied. Same way that T squared be multiplied by something. Can you remember? There's a one approach. This is a one approach. Okay. When you do like this, there's a one approach. See? Can you remember? We did this one. And from that one, we multiplied that by this factor to make that one F. And we found 9. Okay. I want to make sure this 9 is the same as the value coming from the Wilks lambda as well. Okay, that one. See? So then I plug in over here, summation of ni. Ni summation means I equals n1 plus n2. See, in another way, if you want, you can put the capital N for this one. Okay. In this scenario, it's nothing but the n1 plus n2. Oh, that's the same thing I wrote in this format. Okay. See? Same thing. See? P is number of variables. See? And if that's the case, this would be your denominator. They're going to flip and come. Okay. This goes to the denominator. This goes to the numerator. Okay. The same thing being repeated for the F distributed as this one. So I simplify this one, n1 plus n2 minus, and then I plug in my values. Okay. You can remember your lambda 0.25. You calculated. How do you get the lambda? By through this formula. Okay. See? Talking about this one. See? I blew this formula through, and this one we already calculated. This one you can get it same similar fashion. And if you plug in over here, look at systematically they simplify and come up with the same answer. Same degrees of freedom, 2 and 6. That's exactly what I got from the by doing using a different approach, T-squared approach or Hotlin's T-squared approach. It's the Wilks lambda approach. They both should be the same because on your printout, you don't have this one. You don't have this. On printout, you don't have this one. That's what I'm trying to say, that because of this is not going to be there. Instead of using this one, you are supposed to use this one. You can use the Wilks lambda. Or Let's look at other parameters as well. Okay, Wilks lambda, case 1. Let's say that in another situation, in case 2, see, these are the Wilks lambda related cases. This one I already utilized. In a case 2, P have P equals 1 and G greater than 2, you use this formula. But we don't have that one because this is not the case that we tackle right now. The case one under this one, this one. This is how you're going to relate lambda to capital lambda. You know, this is a capital lambda with a Wilks lambda to F. See? It's another way to do that one based on this scenario. You have more than 2 groups, but only univariate. You have a T equals 2, this one. This is how they are related. We saw this one in repeated measures already. This case 4, see, this way. Case 4, case 5, okay. If you have a larger sample sizes or any other cases not being listed here should be approximated by chi-squared, not this time F. That means you cannot simply get the lambda, Wilks lambda, get the natural log of that one, and that should be multiplied by this factor to make this one chi-square, P times G minus 1. See, if you have a large sample sizes, you don't have to go to F. You can straight go to this one. You can tackle that one once you have that one. Okay. When you have a small sample, you tackle like this. Large sample, the reason is this guy, F is a relay, the F and P squared are coming from the members of the same family of distributions, F and T squared. And this one is same as the normal distribution. When you get the normal distribution, if you square, you get chi-square. Okay. If you get the T, if you square, you get F distribution. And the case 6 is if you have a more than two groups, I'm talking about the groups. Okay, in my example, I have only 2 groups. I have 2 groups. They have given A as this one. Okay, sometime in a textbook they might have given in a different letters. That doesn't matter. Stick to one. Okay. So here total, this means capital N, as I said earlier, if you want, you can put the capital N to say the total observations. Okay, this part, or you can write in this fancy way or that anyway convenient. This is a number of groups. P is the number of variables for each group. And instead of this one, you can write this way. See, you simplify this one and you're going to put that G into this parenthesis by simplifying this one, combining these two. And B is this much. This means otherwise. Otherwise means this factor, the denominator factor is only positive. You use that, and by any chance this is 0. If this is 0, you cannot use it at all because that will become the infinitely large. That's why greater than. See? It has to be greater than 0. Otherwise, put 0 in any situation. Okay, that's another one. In the same way, similar like this. This is under that. This everything for. Everything for Wilks lambda. At everything for Wilks lambda. See, under method 1. See, case 1, case 2, case 3, case 4, case 4. Okay. Before go to that one, I think that there's some kind of a mixture in my pages. Because of that, I'm gonna go back here. I'm still on Wilks lambda. Okay. I'm still on Wilks lambda. We're not done yet that one. Once we stop over, I'm talking about here. Okay, in the same one here. Okay, before come to the hot lines, we're not there. B, A, B, minus. For that one, we're not done yet. This is C. For more than 2 groups for the Wilks lambda. Then your degrees of freedom of numerator is nothing but P times G minus 1, degrees of denominator AB minus C. This is how they are related. 1 minus lambda to the power of 1 over B. The B you already calculated. Can you remember? I have a B here. See this B. Okay. That B. Sorry. That B. Gonna go there. And related this one, degrees of freedom you really need in order to get the degrees of freedom on denominator divided by numerator. But for the f, when you put the numerator value here, this value goes here, this value goes there. Okay, flip and go. Okay, see, this is another way to relate it. There's all everything. I talk about the Wilks lambda. Still, we are on Wilks lambda. How they are related to f in case one, case two, case three. See, in case one, see how they are related to f. See, in case 2, these are case 2, case 3, case 4, case 5, how they are related to F Wilks lambda. Case 6, that's the case that I'm talking about. And the method, under the method, second method, how to find the Wilks lambda, this is how they're related. So another way is you're going to get the 1 over 1 plus, you know the between that matrix, you know the W matrix, get the inverse of that one, get the product, and add the 1 and then find their absolute value. That would give you the lambda as well. And method 3, you go ahead and find the eigenvalues of this. You can find the eigenvalues. You don't find by hand, but you run by the SAS and get that one. And get the 1 plus 1 no 1 plus all the summation of all these k equals 1 to p. See p many. If you add like this, that's another way to you can get the lambda. See, I'm still on Wilks lambda. Okay. Wilks lambda. See, Wilks lambda, Wilks lambda. Wilks lambda. See, Wilks lambda. You can get like this way, this way, this way, like that. How they are related to F, like this way. Oh, that is for my example. Okay, this way, this way, this way, this way, or this way. This be here, right? See, like this way. Those are how they are related. There are 3 ways of so many ways of relating to them. 6 methods. And how to calculate that one? There are 3 methods to calculate that one. That's for Wilks lambda only. Let's go to the second one. Second parameter. Hotline lowly trace. See? Method 1. You can get the trace of this guy, which is denoted by, I'm going to use this notation. Or you get the lambda k, sum them up, all the eigenvalues from this guy. B W inverse 1. You know B matrix, you know W matrix. It's a between sum of squares and cross product. It's a within sum of squares and cross product. It's another way we can call the model one. It's the error one. In the textbook, they denote this by H. Excuse me, this one denoted by E. Okay, it's another way. How they are related, case one. See how they are related to. Now this one is not enough. Once you get this one, I want this one to convert it into F. That's the F value that you're gonna see that display over there. See, so S minimum, you get the minimum out of these two, P and G minus 1, number of non-zero eigenvalues in this one. Okay, same thing. And this one P, this one U, degrees of freedom of F distribution would be numerator this one, S degrees of freedom of denominator would be this. If that's the case, F would be T naught squared, which is denoted by the Hartling's law. See, trace divided by S, which is that times degrees of freedom of denominator, which is F. See? That's it. Okay. And something is missing. Okay. This are missing. We have more than that one, but we will mix up my pages. Sorry. Then later on we can talk about the pili. That one we don't have that. Pages are missing. Number one, two, three, okay, and there should be another one. Okay, so give me 1 second. Missing one page. Go to the live. What I'm gonna do, I'm gonna create this up and then I'm gonna upload these notes into the our course homepage. Okay. Okay. So this one, hotline one, then missing save, the desktop scan to. Okay. The third one is the Pillai Bartlett entries. Pillai Bartlett trace. Okay. That's been given by between one type this one minus this one for total, and method 2 that can be even achieved by get that eigenvalues, and then you can arrange like this way that each eigenvalue divided by its 1 plus lambda k goes from 1 to p. All the k's are from this inverse b times w inverse. Okay, and case 1 how they are related to the f, you get the degrees of freedom, same SNT that you calculated earlier for Pillai. Okay, sorry, sorry, the not the Pillai, for the hotline, the early trace. Okay? STU. Okay, same letters. Okay, so this time your degrees of freedom would be this one and this one, and this would be how they are related. Yes. And one more thing in this printout. So we're gonna go through that one pretty soon. Okay, and then I come back and forth with this one. You can say something called the S on the SAS printout. You have it's a minimum between P and the degrees of freedom of the model. Sometimes they call the degrees of freedom of the hypothesis for the univariate one. Okay, not the multivariate one. Not the multivariate one. See, in our case, see this one. See, degrees of freedom. You can see that when we run that one. See that one. M is nothing but the 0.5 times P minus degrees of freedom of the hypothesis, again called the hyper. Okay. This related to an example. Okay, let's look at this. This homework we can do tomorrow. No, this one. And this one for time being. Example, let's say example. So this example, I'm gonna go back to this. 132372466555468881010 Okay, let's go ahead and see how to set up this one. See, we have a two groups. See, we have a two groups. See, we have a two groups. First group has only 3 entries. Okay, so I'm gonna say GP, my input, Y1 and Y2, two variables. Okay, this is the group, this is the Y1, this is the Y2. See, so the first group, 1, 1, 1, 3 entries because of the group 1, group 1, group 1. And let's go ahead and get the first individuals observation for Y1 and Y2. First individual observation for Y1 and Y2. 1 and 3, 3 and 7, 2 and 2. 1 and 3, 3 and 7, 2 and 2. For the second groups, first individual, second individual, third, fourth, fifth, sixth. Their entries, each individual, they're gonna have like a two variables. They have a scores for two variables. Okay, at the same time, we're gonna tackle at the same time, not a one variable. As I said earlier, this is a multivariate. In a multivariate case, maybe two or more than two variables can be included in each group. Okay, same number you have to have in the other group as well. Okay, because you do the comparison. Okay. That's my data. See? So see, these two variables, SA and CSA. Can you remember those variables? See, 4, 6, 6, 8, 6, 8, 5, 10. So that one, then we are using the GLM, okay, generalized linear model, class group in our model, see, Y1, Y2, and GP. And the MANOVA, I'm using the MANOVA, and then I'm going to do the see, H. I mentioned that H. Print A, print H, H and E. You can remember what we call the H and E. A certain point, I mentioned that one, H and E. See, sorry, not here. See, E is W within, see, within sum of squares and gross product matrix, error SSCP. This is B, B is H. See, okay. And let me, let's see. Let's go to our multivariate one. See here. See, see. You can check. Main thing that I'm interested in this one, as I said, these two and Wilks lambda and everything. Mainly that Wilks lambda I calculated. Can you remember? I calculated this guy. I calculated this one in two ways. I didn't calculate. I gave you the formula for that one. You can double check that one as well. Okay. Or you can get it done now and then see that how that can be. The Elias traced. See, this one, Hotlin Lowry trace. Rho is greatest root because that we need that to get the matrix for BW. BW stand for here HE inverse. That matrix you have to find that one, and then its eigenvalues you really need. Okay, in order to calculate these ones, even the Wilks lambda, you can double check and see. But you saw we got 9. We got 9. You saw that we got 2 and 6. Wilks lambda. Here. see 0.25. Wilks lambda 0.25. See 0.25. F value 9. F value 9. How did you get? Through two ways. See, I get that F value by doing like this in a classical way. It's normally we call that on a classical way. See, but multivariate approach, we built up these pieces. When we built up that pieces, we have several methods to get their W1s or the covariance variance matrix for each group. See, we built up that part. And later on, with the aid of that one, we built up this part. And once you get that one, we built up this part, pool variance, pool covariance variance for both of them. Instead of looking at one, I'm going to pool them, multivariately pool them. This is a multivariate case. In a regular one, you know how to pool them, n1 minus 1, s1 squared, blah, blah, like that. But here, pool inverse, and we put that one here, and then we do the calculation, see? And then eventually you get the degrees of freedom 2 and 6 and 9. On the other hand, through lambda, once we get the Wilks lambda, we built up Wilks lambda going through this one. So where are these B and W? So sorry, B, H and E on this printout. Okay, let's go ahead and have a look at it. H and E, where are they? See, what is this? See, look at the E, 6, 8, 8, 30. 6, 8, 8, 30. 6, 8, 8, 30. Did we calculate that one? Yes, see, 6, 8, 8, 30, see. For the error, it's nothing but within or error sum of squares and cross product. See, within sum of squares and cross product or error sum of squares cross product, which is W or E, which is getting through this formula. Oh, we have already done that. On one shot, you can get this one rather than going in this route piece by piece if you're really good in matrices and everything, but you don't have to. But I'm trying to say that whatever you see over there, their theoretical background that I'm exposing over here, see this one, 6, 8, 8, 30. And how about H, 18, 24, 24, 30. 18, 24, 24, 30. See, this is for the, see, they call the H type 2, type 3, sorry, sum of squared cross product matrix 2 group. That's the between one, between groups, group 1 to group 2. See, group 1 to group 2. That one, see, you can see that one, this one already over here. What else? And this one we built up, and then rely everything. I didn't calculate, but when they were already there, but because we mainly focused on that this one, and when this one related to this one, even that we got the F, see, 9 through this route. Is really large. Instead of F, you can work with sorry, chi-square, chi-square. Okay. If you have more than groups, you can work with that one. Hotling, if you calculate this one and find the trace, it will give you the same thing as appeared over there. See, they're all gonna give the same thing. See? I'm talking about F. Okay, not this one, not the same, because when how they related to the once you have this one, how they related to that F. Can we relate? Yes. Can we relate? Yes. Can we relate? Yes. Okay. So what I'm gonna do that I'm gonna straighten up all these pages and then add more and then upload this one under like a new folder. Like even for the repeated measures, some notes I'm gonna upload that way that whenever you can, if you want, you can take a printout or that have a look at it. That one every time that double check that your answers. See? This one 2, 6, and this one. Once you have these and then they are corresponding, see whether this test would be significant or not. See, by looking at this one, you can see one of these all will carry the same probability because of their F value, even though different values for the statistics, it's not what we'll taken into account. All statistics are related to F through certain factors. Okay? Through certain factors. So you saw how they related. See, here related like this. See? Here related like this, see, for the chi-square. Here related like this for the under different conditions. We have everything in our hand, so we cannot make any mistakes. And make sure here we have the summation. Okay, not that capital A. If you want, you can put capital A. That's that one. And then let's go ahead and check this one. See, P. What is the degrees of freedom for this one? Degrees of freedom, I'm not talking about the degrees of freedom for this F value. No, it's a univariate one. What that means? P is 2, we know that one. Why this my degrees of freedom for model? What model? Would be model law hypothesis would be 1. Do you see that one somewhere? See, where is that one? Not in this table, not in here. See, where do you see that one? See, degrees of freedom of model is 1. See, degrees of freedom of model is 1. See, dependent variable y2. See, one at a time. See, y1 separately. If you do that one separately, see, other than do that one at the same time. If you do that one separately, even like a univariate case has been that or displayed over here too. So it's 1. That would be 1. It's 1. See, 1. Okay. And out of that one, minimum value is displayed as a S. Where? S would be that. I'm talking about here. See, S equals 1. S equals 1. Then what? Sure. Okay. Sure. Thank you. Okay. See you on Wednesday. Take care. And look at this one. Yeah. The next one, M. M is 0.5 times P minus degrees of freedom of that model minus 1. So degrees of freedom of model is 1 in various cases. 2 minus 1 minus 1 is 0. So on the printout, if you go ahead and look at it, the printout, that would be 0. Okay, 0. But I use the capital N for, okay, I put the capital N for even for the total number of observation. But here, okay, I'm referring to this, and that's why on this note very clearly, if I go back to that one more time, say, please don't get mixed up. This, even though I say N, you can, if you want, you can say N star or something like that. See, for the total, that's what I want to make sure that they're not going to mix up with what we are trying to talk about here. Listen, N is nothing but 0.5 times the degrees of freedom of residual in the univariate case. See, univariate case. Okay, you go to univariate again. See, here residual is 7. I'm not talking about related to this F test. Okay, here 2 and 6. That's for the overall one. These are see one at a time. Y variable, you have a 2 groups. In this group yn, the other groups y. Y1 and y1 you can compare. And y2 you can compare and contrast. That's what they have doing over here. Okay. This is y1 ANOVA table. This is a y2 ANOVA table. This is the overall the MANOVA table. It's a MANOVA table. It's ANOVA univariate for y2. It's a univariate y1. Okay. ANOVA for y1. ANOVA for y2. MANOVA for y1 and y2 at the same time, assuming that there are 2 groups and within each group there are 2 variables. So then if you calculate that one, 3.57 minus 2, 2. You see 2? Yes. Let's look at another example over here. I got this data. Okay, this data, I can make that available for you. Okay, the multivariate here. Let me see that data. MANOVA. No? If you could, okay, this is related to this one. Okay, that one. The example we saw in the very beginning. I say I'm going to count, not this one. See, MANOVA example. See. The researcher assigned 33 subjects to one of three groups. The first group receives technical dietary information interactively from allowing a two-way, that's a interactive flow information between computer and computers from an online website. See. Group 2 receives the same information from a nurse practitioner. This one from website, this one from nurse practitioner. Third group would be receive the information from a videotape made by the same nurse practitioner. Each subject, each individual or each patient then made 3 ratings. See, each group has now ratings. Difficulty, usefulness, and importance of information in the presentation. Difficulty, usefulness, and importance. The dependent variable Y is multivariate. Why multivariate? Because they were talking about the difficulty, usefulness, and importance. For those three, you're going to give some ratings. See, 3 ratings for each group. There are 3 groups. Okay. So which method would be the best method? We're gonna, if you're gonna check that one under this, can you remember that like when you have a 3 golf balls, and out of that one we ran the analysis of variance. If you have a 2 analysis variance, then ANOVA. Same way this we can run the ANOVA. 3 groups. Okay, doesn't matter. So even though that we were not talking about the 3 groups, that's okay. We can go through example and I can add some more that Wednesday and Thursday. Okay, so see, this is the data. That data, what I'm gonna do, okay, I can put to that load data. Okay. This one. Okay, then okay, I'm gonna go to contents, data. The data I'm gonna create a new folder. You can call that one multivariate. Oops. Mm. Okay, place that multivariate. And then again, I'm gonna check where this data set should be in downloads. Yeah, MANOVA data. Okay, it's already there. You see that folder? Okay, okay, I'm gonna make available under multivariate data name MANOVA, same data set. See? The group, see, usefulness, difficulty, importance, they're gonna rate one group, second group, third group. See, this is the way how that should be, that formatted within that SAS. See, this already been given like that. You see, for the first, see, the first individual in the first group, second individual in the first group, second individual, third individual first group, fourth, fifth, sixth, seven, eight, nine, 10, 11, like that. Yeah. So that I got this one here, then here, see, I got that one. I put in data out, and from the data out, any way you want, I call the maneuver. Okay, the maneuver now I call it the multivariate. If you want, you can check there that means and everything, and then you see you can just, you know, they have that variables being given. Mainly this one is that maneuver part. See, useful, difficulty, importance, and being given by group. The class is group. Group 1, 2, 3, three groups. What are the variables you have? Usefulness, difficulty, importance, and given like that. See, ANOVA, ANOVA H, sorry, MANOVA H, see, for the all groups. See. I can run and check the means too if you want. See. These are for the means for the, that one has 33. 33 individuals. Do I say 33? Yeah. Okay. So usefulness, 33 people, difficulty, all 33, see, important 33, the average, standard deviation minimum, and then mainly that we are interested in this part. See. X lambda, everything, see, 6 and 56, but in this one little bit off, see, for these two numbers, see, 4.12 and 6, and this one, when you calculate, you can see, you can get it done by hand, but we don't have to, see, mainly, see, Wilks lambda, see, that p-value can be utilized, see. So when you set this up, that if you set this up like that, the way that we did over here for two groups, since here three groups, how do you write this down? How do you write this down? At least that this is a maneuver. I'm gonna do that one next time, that in detail on that one too, because we just did only for the two groups. But this example for three groups doesn't matter. Then two, we're gonna do the multivariate analysis of variance. So here, on this one. So, okay, then here that's it. So the maneuver, see, multivariate of variable. Those will have what? More than 3 groups. 3 or more than 3. So here that our H naught should be what? Mu forward, vector mu. Vector mu. Each one has a how many? How many we have that? Two groups. Can you remember? Difficulty. I'm gonna say difficulty for D. Usefulness. Okay, I'm gonna show you mu usefulness and information and importance. For the importance. Like this. This is for the same. Difficulty, usefulness, information. Sorry, importance, difficulty, usefulness, and importance. See, and versus its counterpart. 3 of them, whether they are the same, they will produce the same result. Within each one, we have a 2 variables. See, can you remember? We have a 2 variables. No, so this should be 2 by 1. See, this should be over 2 by 1. See, this is also 2 by 1. See, 1 for AC. What are the variables? No, what are the variables? Sorry, that the first group received technical data. Oh, I'm sorry. No. This is not the right way. I made a mistake. This the 3 groups. I didn't read this one very carefully. Sorry. No. Okay, the 3 groups are the one is on the website. I'm sorry, website. See, website. The other one, nurse practitioner. Third one, video. I'm sorry, video. 3 groups. Okay, within each group, you have a 3. You have a difficulty variable. You have a usefulness variable. You have what's the other one? Importance. See, so you're gonna find it's mean. See, so you have a 3 by 1. Same way over for this group, you have a difficulty mean, usefulness mean. This one. See, same way, difficulty, usefulness, and importance. See. Mean. This one bar. See, equals 3 by 1 d bar u bar. This one equals d bar u bar and I bar for that group 3 by 1. See whether they are equal to each other. See, that's what you are trying to test. Versus its counterpart should be what? At least. See? At least. See? HA. At least. See? 2 of them are different. That means, see, I'm gonna say mu I vector, mu j vector, I not equals to j. See, not equals to j. At least they not equals. See, where I and j can take what? Either website, either nurse practitioner, or video. That group. That's the hypothesis we're gonna check over there, because that we can say whether we're gonna reject this one or not by looking at this p-value. See, looking at this p-value. See, p-value, you can say that we reject h naught, but that doesn't mean that you don't know which one is important, and then you have to do the multiple comparison. We're going to talk about that one in detail next time. Then come go along with that homework. So if you little bit that jump into that homework too, that look at the homework, we are using the same data set, and if you pull out that homework, that one, little bit have a look at it, 5 minutes, and then we can stop because I have to jump into the class. I'm gonna put all the notes uploaded into this one, in that you're not gonna miss anything, and we have recorded everything. Okay. Homework 3. Okay. So we are using the kind of like a same. It's not hard because that it has only one question, I think, here actually. See, you have to run the multivariate analysis, perform the multivariate analysis of variance using the proc element, this one, and discuss data call to fix any problem that arises with the data. Same like descriptive analysis, just give the descriptive statistics for independent and dependent variable. Discuss mean, variance, any outlier distribution. The mainly this one. Look at some smokers claim smoking is an appetite. So you don't have to stick to this one. But we are trying to do, see here, in the way that I set up. Okay, you have to set up a maneuver. Okay, so I set up like this way. I get all these some variables. See, AD39W. I got AD39W, AD41, AD42, AE27. These variables. And these variables are related to how active they're gonna be. They are, see, physical activity that they done that one. See, average length of the time walk for transportation, time walk at the least 10 minutes for the leisure, past 7 days, average length of time walk for the leisure, and the time per day of moderate physical activity, number of days the vigorous physical activity in past week, number of times ate cake, pie, cookies last month, number of times ate ice cream, frozen desserts last month, household total annual income, but up to here AC 14. See, this one less than one. I see if they were less than one, I put the zeros for that one and get the maximum of that one. See, max of this one equal to 0. See? Then even from the max of these activities, 0, then you can say sedentary is 1 or sedentary 0. Then as we used to do that on some places, that if you have less than negative values, you can take that out from that one. Later on, that if you have a missing value, you know how to remedy that one by replace them with the if you mean value or average or zeros or whatever, that we know how to remedy the missing values. See, and income, I'm gonna the group into this one, low, middle, and up and high, like that. Okay, and later on, especially that I'm gonna do this on it. Then I got this one too. I pass out this one, that the same way that we have that one. From this one, I got this one together. We have already have those variables from even the homework one. I use in that one, I got all these, and their average I call the mental. See, mental situation. See, and that one I'm gonna utilize as one of the variables. See, one of the variables is another variable, the BMI, and I can look into, see, 3 predictors. If you want one, not one predictor, 3 predictors you can tackle at the same time. See, tackle at the same time. See, these are 2 classes. See, classes mean group. See, 3 predictors. See, This one, first look at this one. This one predictor, see, let's say sedentary. See, that's the class. Okay, you can remember the way that we put in over there. You have a two option that class. See? So then inside, see, mental and BMI. See, these are the variables that why you not gonna that be physically active gonna be the being explained by these two variables. See? The way that any way that you can build up any way that you want, two variables. Okay, these two variables, for this guy, that's the group. See that? See? So give me a little bit. I'm gonna run this one. I don't need a factor analysis, but I keep that one over there too. Let's see. Okay, that one, that test, that test. Mm, mm, yeah, that data. That's a BMI. Do we have a BMI? Test. Inside the test, we have that BMI. And 3 sedentary. So these ones for see that variable y1 like the same way that we had earlier y1, and this one for body mass index, see, dependent variable. This one for the dependent variable mental. We built up that one. And then we have a two groups. Sorry, two groups. Each group has what? See, one is sedentary and the other one is active. See, this one, two group. Within that one, two variables will be taken into account, and then see that how they affect to that sedentary and the activities per day. See, the way that built up. See, the mental. See, mentality per particular day, and the BMI, the body mass index, the way that I set up. So you can that simply that one later on, that even the three predictors we can look at into see those two, but you see three predictors. 1, 2, 3. All these how they're gonna affect to this one. See age and everything, that how they are. What's the impact on that one? See mental and BMI. These are the variables. See? I think we're missing over here another class. We should have this one too. Three classes, see, three predictors. See. These two variable, each one has. So let's run this one and see. Oops. Oh. These two. Yeah, one. Oh. Yeah, this one. See. Mainly we can look into this one. See. This is the age. This is gender. I just keep like that. Okay. Then this one, sedentary versus this one, the age versus this one. Sure. What about this picture over here? See, this one here for the sedentary. See, for the sedentary. This one for the see. This one 6. That one. This one for the age. This one for the sedentary. See, sedentary, age, and sex. See, 3 that. This MANOVA table will be built up because that you're going to have a look at it at the same time. See, you can, if you want, you can have a look at it. This all these at the same time. See, rather than one at a time. See, this one versus these two, this one versus these two, this one versus these two. But each one, this one, these are the variables in each group. Do we have a 2 groups for this one? Yes. Do we have a 2 groups for this one? This one. You can group them. See, this one. See, or that you can take like a with the like each number would be like a group like that for the in a continuous case. This one for sure that male and female. This one already we set up. See, sedentary. See, based on this information. See? So you can run like that, and then so I'm gonna go through that more detail in that one. We have plenty of time to go through and the multiple comparison in like that. So you can think about that, build up something very simple in the very beginning, like one variable, sorry, 2 variable or 3 variables versus one predictor, one dependent variable, one group. No, same way that, can you remember that we did over here? See, see? One group, sorry, see? One group, 2 variables. See? Here, same way that you can do that one here, that later on here. See. Here, see, here 3 variables. So here 3 variables, 3 variables, 3 variables, 3 groups. But the 3 groups are already mentioned within the group. Within the group, it's already been that group, and then all the data has been properly grouped according to that their particular group, in which that there are 3 groups in which that first group gonna be that they were participating in that online, go online and then have a look at it, those get the information. Second one that you're gonna just listen to that, they give a lecture by that this nurse practitioner. Third one that they're the same nurse practitioner gonna make a video, and then they're gonna play, it's gonna be played for the people. So that one be already more, that one the same way here, mainly here, that you can think about this one. Sorry, this one, think about something like that. 2 variables and 1 group. The group has, the group means like it has 2 parts, 2 groups actually. One group active group, the other group is sedentary. So we can continue this discussion, and then mainly the major thing I'm gonna do that I'm gonna add more notes to this one and then upload to the system. If you guys don't have any question, I'm gonna stop over here. Okay, then we can continue the same discussion on Wednesday. Okay, you guys have a good night, stay safe and be well. Okay, take care.
Thank you. Have a good evening.
Have a good night, take care, bye, take care, good night.